Okay, we're going to continue on in chapter 21 with alkylation at the alpha position. So we're going to go ahead and switch over to blue. There we go. And look at adding R groups alpha to the carbonyl. Right? We're going to see some SN2 mechanisms, so those restrictions will apply. Right? We know that tertiary alkyl halides won't work. E2 will dominate. We'll see some secondary. It just depends, but definitely no tertiary. The aldol reaction would compete, so we must use a really strong base. For this one, we're going to use LDA and NaH. And regioselectivity will be something to look for. Okay, so let's say let's look at the example that they're starting off with. So let's take an asymmetric ketone, right? So we're going to have this methyl cyclohexanone. If you want to add an R group to the more substituted side, you can. And if you want to add an R group to the less substituted side, you can. But you have to be thoughtful about your reagents and temperature. So one of them is going to be considered the thermo product, and one will be considered the kinetic product. Now, the thermo product is the more substituted. And look at what you see with the enolate that forms. If you have an enolate where your new group is going to add to the more substituted side, that enolate's more substituted, right? More stable. And if we go the other way, it's a little bit less stable, but it's also less sterically hindered, right? Because there's just a hydrogen there as opposed to whatever this R group is, as opposed to the methyl that this methyl right here that we're using in our example. So there's pros and cons to either, and we can manipulate that or exploit that. Right? It's similar to what we saw when we had the 1,2 versus 1,4 addition of a conjugated diene. One has a higher activation energy, but is overall more stable. The other has a lower activation energy, but isn't quite as stable, right? Kinetic versus thermodynamic products. All right, so if we want to go to the less substituted side, right, that's over here, we're going to use the bigger base. Lithium diisopropylamine is bigger and bulkier, and we're going to keep it cold, 78 degrees. Now, I don't expect you to know the temperature necessarily, but I expect you to know it's cold, right? That cold is going to keep us from being able to get over this big blue hump, right? The colder it is, the more likely we're going to go through this red pathway. Then your second step will be the same for both of these. You're going to add in your alkyl halide that you want to attach. Now, if you want to go to the more substituted side, you need to use a much smaller base like sodium hydride, NaH, right? Because it's just a little hydride that is getting in there and deprotonating. So the sterics aren't that critical, right? And it's going to be quote unquote hot. Now, 25 degrees isn't hot, relatively speaking, but it's much warmer than -78. So if we have sodium hydride at warmer temperatures and add in Rx, we can get the more substituted product. Okay, right, so we want to make sure that we highlight this. It's warm, it's sodium hydride. That's going to give you the more substituted product, where the kinetic product will be favored if you use the bigger base and keep it cold. Okay, that gives us a lot of control, which we love. I am not going to ask you the mechanism of these, but because it's something you've already done a bunch. It's a deprotonation with the base and then an SN2 reaction, right? It's something like this. H base. You may have to do it in your homework. You make your little enolate ion. Since it's a C attack, you don't have to draw the resonance structures. No need to. And then RX, you'll come in. Let's make that a little bit cleaner. RX, you'll have the SN2 backside attack, right? And that will be your new alkylated product, okay? It's an easy reaction. The main thing is to know your base and temperature choices. Be very useful in synthesis problems. All right, we're going to look at two more reactions where we're going to alkylate at the alpha position. But these are very special synthetic strategies. So the first is malonic ester synthesis. And it starts with, what's nice about this one is it always starts with the same starting material, this diethyl malonate here. And once you get used to drawing it, it will get very monotonous, not monotonous. It will get easy. There we go. This diethyl malonate, something that you might notice, has very acidic protons right here because there's going to be, if you remove them, that negative charge will be stabilized on both sides, but through both carbonyls. So this starting material will lead us to this kind of interesting product right here, where we are going to wind up with a 2-carbon carboxylic acid and then whatever R group we want to add on to it. All right, so if we treat this with now we remember a strong base when it comes to these distabilized enolates, it can be any of your strong bases. They all wind up being irreversible. So you're typically going to see one that matches that OET group. So you're going to use sodium ethoxide, right? And so you don't have to use LDA or NaH. You can, but you don't have to here. And that is going to leave you with this enolate, and it's irreversible because it's so much more acidic. And then from there, you can add in whatever group you want, and you're going to have this interesting little alkylated diethyl malonate. Now, why would you want to do this? This has a very kind of unique property in that you can decarboxylate. So we're going to kind of make this a little bit smaller. Here we go. If you treat this, first of all, you're going to do something that really takes 2 steps. You're going to use, but I'm going to show them, I'm sorry. It's going to be 1 step, but I'm going to show them in pieces first. All right, you're going to hydrolyze your esters, right? When you have an ester and you take H plus and H2O, right, that is going to leave you with carboxylic acids. That's something that you know from the last chapter. Now, this is really what is special here. If you heat this malonic ester derivative, or I'm sorry, malonic acid derivative, it is going to lose CO2. Right? It's called decarboxylation. And you're going to wind up with, right, let's just highlight, you're going to lose this whole piece right here. And so you're going to wind up with ROH, right, where only these 2 carbons came from the original malonic ester. Now, how does that happen? We're going to look at it, but I'm not going to ask you to know this mechanism. All right, you already know the hydrolysis, right? This is something, again, we covered in the last chapter. But from there, when you heat it, because you have free rotation around that single bond, you are going to have this kind of arrangement, especially because hydrogen bonding will help get it in that arrangement. And then you get this rearrangement process. It's pericyclic, so kind of similar to Diels-Alder. And it rearranges such that you lose CO2. It's cool, it's interesting, but you don't have to show it. It does leave you with an enol, but that is going to tautomerize. So you are going to wind up with that 2-carbon carboxylic acid with whatever R groups you wanted. So what would that normally look like? Let's see. Let's maybe not use a highlighter. There we go. You'll have your malonic ester. There we go. And on the arrow, you would have something like NaOET. And then let's say we wanted to add 4 carbons. And I'm going to use bromine, but of course you could use chlorine or iodine. And then in step 3, I'm going to use H3O plus and heat. That's going to decarboxylate. Now, I know that my product will have this carboxylic acid 1 and 2, and then 3, 4, 5, and 6 will come from that RX. So then we'll have 3, 4, 5, and 6. Make sure you count your carbons. That is definitely some place where people often mess up, is they wind up cutting out, sometimes adding, but usually leaving out carbons. Now something that is, oh, and here you go. So you can see one way we can look at it. Now, something cool about this, it can be dialkylated. So once you get to this step here, where you have added your first R group, you have another acidic proton. So you can do it again, right? You use that sodium ethoxide again. You have to do it sequentially. You can't do it all at once because it's not going to remove both protons. And then you can add a different R group. So we'll use R prime here. And then if you treat it with H3O plus and heat, right, you're going to wind up with these 2 carbons here, OH, and then you'll have the R group that was there that you added first, and then you'll have your second R group. What you want to make sure to pay attention to is these 2 carbons came from the diethyl malonate. Just a couple more examples here. How you can use this benzylic bromide. Oh, I'm sorry, that's a different reaction. Hold on. Oh, I thought there was an example. Okay, so we're going to do an example before we move on to the next reaction. Give me your page. There we go. Okay, so we're going to kind of work backwards here. What if we wanted to make something like this? All right, if we want to do a little retrosynthesis here, we want to think about what are we going to add to our malonic ester. All right, now we know a few things. We know that we're going to start with sodium ethoxide. We're going to add an R group. We're going to hit it with sodium ethoxide again. And then we'll put on the second R group. We'll come back to that. And then the very last step, because we have that carboxylic acid, will be H3O plus and heat. You don't want to do this till the end, because if you do this before the end, then you have a carboxylic acid. You can't do the second addition here, or second substitution. So I want to analyze this starting material. These 2 carbons are these 2 carbons. So I am looking at, excuse me, adding this piece here and this piece here. Sometimes it helps to circle or highlight so you can see exactly how many carbons should be in your reagents. All right, so I'll go ahead and start with the top one, and it's going to be a 5-membered ring, a carbon, and then a bromine out there. Okay, now the last step, this one would be tough to do. You'd really have to try to help that SN2 go along because there's a lot of steric issues. But if I wanted to do it this way, what would be the starting material? Well, I have 1, 2, 3, 4 carbons, and it's adding at the second position, so I'm going to put my bromine right there. And this could be a way that I could make that product. Definitely will give you a lot of practice with this. I know there's some on the old homework assignment that I'll put up. Okay, the next synthesis is very, very similar. It's the acetoacetic ester synthesis. And so it looks very, very similar, but it starts with a slightly different starting material and therefore gives you a slightly different product. So you only have an ester on one side. And so at the end of the day, you aren't going to make a carboxylic acid. You're going to be adding on to acetone, essentially. All right, so you will have an R group here. We'll wind up losing all of this. So how does this work? Well, first, we are going to treat with our base. Right, and that is going to give us that alkylated alpha position. No, why would just treating it with base do that? That's going to give us an enolate, of course. Then we are going to mix in Rx for our substitution, and that will give us our alkylated alpha position. And then from here, you can treat with, if we're just doing one R group, you can treat with H3O plus and heat. It will still decarboxylate because of the position of this carbonyl. The H3O plus will hydrolyze this. Then it can swing around and you'll still get that same decarboxylation. Okay, so let's do a practice one with that before we move on. So let's say we come across this. And I'm going to go down. Here we go. 1, we do sodium ethoxide. And let's say we start simple. Maybe just an ethyl bromide. And then number 3, let's do it again. Because we would still have another acidic proton there. And let's see. Let's do something a little bit more exciting. I don't know if it's that exciting. We'll do this iodide. And then 5, we'll do our decarboxylation step. Let's predict the products. Now, again, we know that with acetoacetic ester synthesis, we're essentially adding on to acetone. This carbon right here is part of this starting material. So now we want to add on to it. Excuse me. The first thing we add on, of course, is that ethyl group. Okay, so we had 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Great. Now we're going to add this piece on. So we have 1, 2, 3, 4 carbon chain with a methyl. So it's going to be 1, 2, 3, 4 carbon chain with a methyl. All right, so you just want to make sure that all of your carbons wind up there. So we have 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. These are, as far as product prediction goes, are really nice because this is a very unique starting materials. But they can also be helpful in more of your large synthesis problems. Your extra credit will give you more practice at that as well. All right, we will hit conjugate additions in the next video.